Section 3.3, Newton's second law of motion. Before we talk about second Newton law and the variables involved, let's review first Newton law. So when F net is 0, we have an object at rest will remain at rest. So velocity will stay 0. And if the object is moving, is in motion, it will continue to move in a straight line at a constant speed. That means with a constant velocity. In both cases, since that there is no change in motion, there is no change in velocity, acceleration is 0. Now, what would happen if F net is 0? What would happen if we apply an unbalanced force on an object? The answer is the object will accelerate. Now, at what rate? Does that acceleration depend on a force? Does that acceleration depend on a mass of the object that we are applying the force? What is the direction of that acceleration? Those questions we can answer by doing a few experiments. As any science experiment, we have variables and control variables. So we change variables and we keep constant some other variables to study one variable at a time. So if we want to analyze the effect of the force in acceleration, we should keep the mass the same and change force. That's what we do in this experiment. We have the same card with the same mass, and we apply a different force, and we'll see that card will accelerate differently. The bigger the net force, the bigger the acceleration. The smaller the net force, smaller acceleration. So it's clear that acceleration is in a direct proportional with the net force. So in a practical point of view, we can compare two cars with almost the same mass. The car with a powerful engine will accelerate faster compared to the car with a smaller, normal engine. The net force acceleration graph is a linear graph, and the slope of that graph represents the mass. It is very clear that it's a straight line, and the slope of the straight line is a constant, and mass should be constant. The line must go through the origin, since when the acceleration is 0, the net force must be 0. Here is another experiment with an air truck. So if you see on the holes of that air truck, the air will blow to keep the cart almost floating to minimize the friction. So if we apply a different force on a cart that is at the same mass, you're going to see the acceleration is going to be double for double the force. In another type of experiment, we analyze the effect of mass into acceleration. By keeping the force constant, we can change the mass and try it how different mass will affect the acceleration. We have similar test as before. So we have a cart, but this time we have a force constant but mass different. In a cart with a smaller mass, you'll see the acceleration is bigger. And with a cart with a bigger mass, the acceleration is smaller. In a practical point of view, you can actually experiment this yourself. While you're shopping at a store, a grocery store, for example, you can accelerate, speed up the cart, shopping cart, compare that much easier compared to when the cart is fully loaded with a bigger mass. Now, if we want to compare two objects that have a different mass, so a race car and a truck definitely have a different mass. Truck is more massive. However, the engine, they do have almost the same powerful engine. So the force acting on those, accelerating force acting on those objects, race car and truck, is almost the same. However, we know that race car is going to accelerate much faster compared to a truck because truck has a much bigger mass. Graphing acceleration versus mass will give you a graph that shows a reciprocal relationship. So the smaller the mass will be a bigger acceleration and vice versa. The bigger acceleration will be at a smaller mass. Bigger the mass, smaller acceleration, etc. Let's explain the experiment with a cart again, but this time we have a double mass while keeping the force the same. You'll see that acceleration is much bigger with a smaller mass compared to the cart that are in a second experiment that is double the cart, half of the acceleration. Newton's second law of motion says if the net external force on an object is not zero, the object will accelerate in the direction of the net force. The magnitude of the acceleration is directly proportional to a magnitude of net force and inversely proportional to a mass of the object. Mathematically, we can express the second law of motion as acceleration is equal to a force divided by mass, or force is equal mass times acceleration. With this formula, force is equal mass times acceleration, we know the unit of mass is kilogram and unit of acceleration is meter per second square. We know that the unit of force now is 1 kilogram times meter per second square. So that is an international standard unit that is derived by a base unit of kilogram, meter, and second. Here is a practice problem. A force exerted by a stretched rubber band produces an acceleration of 5 meters per second square on an ice cream carton of mass 1 kilogram. When a force exerted by an identical rubber band stretched at the same amount, so the force is equal, is applied to a carton of ice cream of mass m2, it produces an acceleration of 11 meters per second square. What is the magnitude of the force applied by the rubber band? So what is given is A1 5 meters per second square on a carton 1. Mass of the carton 1 is 1 kilogram and force is required. Based on the second Newton law, force is equal mass times acceleration. So that means the force is 1 kilogram times 5 meters per second square is 5 Newton. That's the answer. Now, if we want to know what is the mass of the second carton, well, we know A1 and M1. We know A2, acceleration of the second carton, but we don't know the mass. But we know something, that the force is the same because we're using the same rubber band. So that means the force F1 is equal to F2, which is equal M1A1 is equal to M2A2. From here, we know M1 we know A1, we know A2. We solve for M2, which is M1A1 over A2, is equal 1 kilogram times 5 meter per second square divided by 11 meter per second square, which both of those cancel, meter per second square and meter per second square. And what is left is 0.45 kilogram. And that's the answer. Here is a practice problem that involves direction of the acceleration. In which direction does the object accelerate? Explain. Let me explain. I'm going to explain by saying why those options are not an answer, are not true. Let's start with the A. A is not true because if that was true, then F1 and F3 has to cancel each other, which make F1 and F3 the same magnitude but in opposite direction, which is not true because F3 is longer than F1. So we do have a vertical component, vertical resultant. B is not an answer because for the same reason. If the F1 and F3 has to add up together, will produce a resultant downward, not up. So the B would not be an answer. C is a nonsense option. There's no way that C would be an option at all. And E is not true, not correct, because you cannot ignore F2. If the F2 would not exist and we have only vertical forces, then E would be an answer, which in this case it is not because F2 exists. So the only correct answer is D. D because the resultant of F1 and F3 would produce a vector that is downward, and if we add vector F2 and sum of F1 and F3 would be something that in that direction of A. Here's another practice problem. There are 3 people pushing a 752 kilogram boat and each exercising a 180.5 Newton force parallel to a dock. What is the acceleration of the boat if they all push on the right? So all of them are pushing at the same direction. In order to, let's see what is given, what is required. You have a mass of the boat, 752 kilogram, and you have force that Mike, Larry, and Kobe is pushing. Each of those forces are 180.5 Newton, right? So acceleration is what? F net divided by mass. In order to find F net, we just have 3 times of that force. So 3 times 180.5 Newton on the right is 541.5 Newton right. As we know now F net, we are ready to calculate acceleration. So acceleration is F net divided by mass is a 541.5 Newton right divided by 752 kilogram will produce an acceleration of 0.72 Newton per kilogram, which is the same as meter per second square on the right. So it's 0.72 meter per second square right. B. What is the acceleration if Mike pushes on the right and Larry and Kobe on the left direction? So here's a diagram of the forces. And here is what is given. Again, mass is 752 kilogram. Force that Larry and Kobe is on the left, 180, the same, 180.5 Newton. And Mike is pushing on the right, 180.5 Newton. What is acceleration? So the same way, we calculate what is net force, which is sum of all forces. So now we have 2 on the left and 1 on the right. 180.5 Newton right plus 180.5 Newton left cancel each other. So what is left here is 180.5 Newton left. Now we are ready to calculate acceleration. 100.5 Newton left divided by 752 is 0.24 Newton per kilogram left, or as I said, Newton per kilogram is equal to a meter per second square. And that's it. Here is another practice problem. A 64 kilogram runner starts walking at 3 meters per second east and begin to speed up for 6 seconds, reaching the final velocity of 12 meters per second east. Calculate the net force acting on the runner. Here is what is given. Mass 64, initial velocity 3 meters per second east, final velocity 12 meters per second east, time interval 6 seconds, and net force is required. So net force is equal mass time acceleration. We have mass, but we do not have acceleration. So we have to calculate acceleration first, which is a v final minus v initial divided by delta t. We plug those numbers in the formula, and we get 1.5 meters per second square east. Now we are ready to calculate F net is equal MA, 64 kilogram times 1.5 meters per second square east is 96 Newton east. Here is a similar problem, but now is a slowing down. During the road test, a driver brakes a 1,420 kilogram car moving at the 64.8 kilometers per hour west. The car slows down and it comes to a stop after moving 729 meters. Calculate the net force acting on the car. I want you to pay attention to these units because it's very important. 1420 kilogram is a standard unit, but 64.8 kilometers per hour is not. And now the distance or displacement is 729 meters, which is a standard unit. So the first thing we need is to convert it. Initial velocity is 64.8 kilometers per hour, which makes 18 meters per second. So in order to calculate F net is equal MA. So we have final velocity 0, which is the car come to a complete stop. Displacement is 729 meters west. And in order to make it easier, we can make west as a positive, since we have both west and west. So acceleration is 0 minus plus 18 meters per second square divided by 2 times 729, which is minus 0.22 meters per second square. So since that we actually use west as a positive, now if we reverse it, that is going to be east. So it's going to be 0.22 meters per second square east, which makes sense. Now we can calculate F net is equal to M times A. It's a 1220 kilogram times 0.22 meters per second square east. That will make 315.6 Newton east. As a matter of fact, if you want to go over and make sense out of this problem, you'll see that when a car starts braking, the force of friction slows it down. So that means force of friction has to be opposite direction. So acceleration has to be in opposite direction of the previous direction of the motion. So that's why car is moving toward west, and acceleration, which is slowing down acceleration, is in the opposite direction. It is toward east. So that's why the force of friction is always against the motion, and now it is 315.6 Newton against the motion, against opposite of west is east. So that makes sense. Solving a pulley problem is very long and complex, and I want you to pay attention to this one. Pay attention to steps because they are very important to help you not to get confused and not to make mistakes. Calculate the acceleration of the cart and the tension on the rope. Given the following assumption, there is no friction acting on the cart. The first thing that you can do is to label the masses, tension, and acceleration. Next one is write what is given, what is required. Mass 1 is 1.2 kilogram, mass 2 0.6 kilogram, and acceleration and tension is required. As solving any dynamic problem, you have to draw free body diagram. Let's start drawing a free body diagram of object 1, the cart. So object 1 is a force of gravity. Label it 1. Make sure you don't forget that. It's a normal force acting on the cart. And there's a tension pulling the cart on the right, and that will be a positive direction. So the direction of the motion is the direction of the acceleration, and is a direction that we label it as a positive direction, regardless. It is left or is right, is up or is down. So choose the positive direction and apply the appropriate Newton's law on each axis. What does this mean? That means that you can apply first Newton's law if there is no motion on that axis, or is motion at a constant velocity, which in this case is not true. Or you can apply second Newton's law when there is acceleration. So in a first Newton's law, we can apply on y-axis because we know the cart is not moving up or down, it's moving horizontally. So F net has to be 0. So F net is sum of all forces. In this case, we have 2, Fg1 and Fn1. We can follow the positive direction, and positive direction, since that is a first Newton's law, we're going to keep it traditional, positive up. So Fn is in direction of the positive, so it's going to be positive, and Fg1 is opposite of positive, so negative. Now we have Fn1 is equal to Fg1, and we're going to leave that here. However, when we're going to study friction on chapter 4, we will use Fn. But for now, we're not going to calculate anything. Just leave it. Now, F net x is equal to m1a, is object 1, is a mass 1, is accelerating in that direction. So F net is equal to sum of all forces on x axis, which we have only one force on x. So F net x is equal to T1, that is equal to M1A. So we can follow the positive direction. We can say T1 is positive and acceleration is positive as well. So we can write equation number 1 as a T1 is equal M1A. So plus T1 is equal plus M1A. We'll continue with the solution. Now we're going to focus on object 2. If you take a look, the acceleration regarding to object 2 is downward. So that's why we label that direction of the acceleration as a direction of the motion. That's downward. Now we can draw and label the object 2 free body diagram. Object 2 free body diagram is simple because we have only one direction. It's FG2 and T1. The direction of the acceleration is down, so then we can use a second Newton law on that direction on a y-axis. So F net y is equal M2A, and F net y is the sum of all forces, which is Fg2 plus T1 is equal M2A. Now take a look. The positive direction is down, so Fg2 is positive and T1 is negative. So we can say Fg2 minus T1 is equal to M2A, and that makes equation number 2. Now next step would be add those two equations together, equation 1 and equation 2. Make sure we did not make any mistake, so both acceleration has to be positive. And another thing that you have to look is tension has to cancel. So Fg2 minus T1 plus T1, they will cancel. So on the left is a Fg2, and on the right we have M1A plus M2A. So A is a common, we can factor it. So there's A, M1 plus M2. Now we can solve for A. So A is Fg2 divided by M1 plus M2. And we can plug those numbers in that formula. And we can find acceleration is 3.27 Newton per kilogram or meter per second square in that direction that is labeled. Now, in order to calculate the tension, we go back to equation number 1, which is the easiest one. So tension is equal M1A. We do have M1 and we have A. So we can actually plug those numbers in the equation, and we find that tension 1 is 3.9 Newton. Now, force of friction has to be taken into consideration when we calculate acceleration and tension. Let's start with labeling the same way. Object 1 and object 2, direction of the acceleration and tension. Write what is given, what is required, and then draw and label the object 1 free body diagram. The difference here is we do have force of kinetic friction, which is the opposite direction of the motion. So the motion is on the right, and force of kinetic friction has to be on the left. We choose a positive direction, which is direction of the motion, and for y-axis, which is not moving, it's no motion on y-axis, we keep it simple, traditional, positive up. And for x-axis, the direction of the motion is the direction of the acceleration, which is going to be a positive direction. Let's start with the first Newton law on a y-axis. Fn1 is positive. That's why it's is positive, because it is in a direction that we chose to be positive. And Fg1 has to be negative. Now on a y-axis, we're done. With the x-axis, there's an acceleration. So apply second Newton law, F net x is equal m1a. F net is equal to sum of all forces. In this case, we'd have two forces. Positive is T1 and negative is Fk. So T1 minus Fk is equal m1a, and that will be equation number 1. We will continue with the object number 2. We take a look. There's acceleration here that is very important to look. Acceleration is down, so will be a positive direction. We do pretty much the same way. So this object is not affected by friction at all. So everything that we did at A, it's at B as well. So Fg2, T1, direction of motion is down. That will be a positive direction. And then we apply the Newton's second law in the y-axis. So F net y is equal to m2a, and F net y is equal sum of all forces. We have two forces on that y-axis. So Fg2 is going to be positive, T1 negative, and m2a is positive because it's the direction of the motion that we already chose. So Fg2 minus T1 equals to m2a, and that will be equation number 2. And the last step would be we add the system of two equations. You see that T1 will cancel. On the left is Fg2 minus Fk. On the right is m1a plus m2a. We factor a and we solve for a. So it's Fg2 minus Fk divided by m1 plus m2. We plug numbers on that formula and we find acceleration is 2.99 Newton per kilogram or meter per second squared. We can calculate tension on a string using equation 1. We move Fk to another side of equation, that minus Fk becomes plus Fk. And we plug numbers and we find T1 is equal 4.1 Newton. And that's end of the lesson.